This section discusses the sampling distribution of the difference between two sample means for independent samples. Many applications involve two populations. For example, we may want to compare males with females, patients with healthy persons, and new drugs with existing drugs. In these examples, we need to deal with two populations. For independent simple random samples from two populations, we mean that one simple random sample from each population and each possible pair of samples is equally likely to be the pair of samples selected. Let's use an example to illustrate what independent simple random samples are. Consider two small populations. One contains 3 males and the other contains 4 females. Let's take a sample of size 2 from the male population and a sample of size 3 from the female population. Let's list all possible pairs of independent samples. Because there are 3 males, and we want to take a sample of size 2, there are 3 different possible such samples. There are 4 females, and we want to take a sample of size 3. There are four possible samples of females. If we combine one male sample with one female sample, there are in total 12 possible different ways to obtain the final samples. There are 12 possible different samples are equally likely to be chosen. The chance of obtaining any particular pair of independent samples is 1 over 12. When we say independent simple random samples, we mean that we get one sample out of these 12 possibilities with probability 1 over 12. Let's look at one example involving two populations. Are the mean salaries of college faculty in private and public institutions different? In this problem, we want to compare two populations. One contains faculty in private institutions, and the other one contains faculty in public institutions. The variable that we are interested in is salary. Here, we want to compare the mean salary of faculty in private institutions with the mean salary of faculty in public institutions. Let mu1 and mu2 denote the mean salaries of faculty in private and public institutions, respectively. The null hypothesis is mu1 equals mu2, and the alternative hypothesis is mu1 not equal to mu2. It is a two-tailed test. This diagram explains what we need to do to solve this problem. We need to take samples, one sample from each population, calculate the sample mean for each sample, and then compare the two sample means. Because a sample mean is expected to be close to the population mean, if the two samples are close, we expect that the two population means are also close. If the two samples are quite different, we suspect that the two population means are different. Suppose that the sample contains 35 faculty members from private institutions and 30 faculty members from public institutions. The table lists their salaries in thousands of dollars. We use notation N1 and N2 to denote the sample size of the first and the second samples. Use X1 bar and X2 bar to denote the sample means of the two samples. Clearly, N1 equals 35 and N2 equals 30. We can also calculate the sample means. X1 bar is $98.19 thousand and X2 bar is $83.18 thousand. Here, X1 bar is larger than X2 bar. There are two possible reasons for this. First one, the mean salary of faculty in private institutions is higher than the mean salary of faculty in public institutions. Secondly, the difference is due to the randomness of samples. If we take different samples, it is likely that the sample means are equal, or even x1 bar is smaller than x2 bar. Is the difference significant, or is this difference large enough to make us believe that the population means are also different? In order to answer this question, we need to know the sampling distribution of x1 bar minus x2 bar. Suppose that x is normally distributed variable and on each of two populations. Then, for independent samples of size n1 and n2 from the two populations, we first know that x1 bar minus x2 bar is normally distributed. Additionally, we also know that the mean of the difference of sample means is equal to the difference of population means. In this sense, we may say that the difference of sample means is an unbiased estimate of the difference of population means. The standard deviation of the difference of sample means is the square root of x1 square over n1 plus sigma 2 square over n2. Here, sigma 1 and sigma 2 are sample population standard deviations for the first population and the second population respectively. Here, we will not discuss mathematics. The sampling distribution of the difference of sample means is given directly without explanation. It is enough that we know this result. Generally, for hypotheses involving two populations, we want to compare the two population means. The non-hypothesis is mu1 equals mu2. There are three possible alternative hypotheses, namely two-tailed test, mu1 not equal to mu2, left-tailed test, mu1 less than mu2, and the right-tailed test, mu1 larger than mu2. You can see that this is very similar to the hypothesis for one mean z-test and one mean t-test. The difference is that we compare mu1 and mu2 now. In the previous 8 problems, the population mean is compared with a given number. We can also construct confidence intervals for the difference of population mean mu1 minus mu2. We will discuss the procedures to calculate confidence intervals later. Right now, we just look at how to interpret such confidence intervals. When the endpoints of the confidence interval are both positive, for example, suppose that a 95% confidence interval for mu1 minus mu2 is 3 to 5. We can say that we can be 95% confident that the difference of mu1 and mu2 is somewhere between 3 and 5. A better explanation is that we can be 95% confident that mu1 is somewhere between 3 and 5 greater than mu2. When the endpoints of the confidence interval are both negative, for example, suppose that a 95% confidence interval for mu1 minus mu2 is -5 to -3. We can be 95% confident that mu1 is somewhere between 3 and 5 less than mu2. When one endpoint of the confidence interval is negative and one is positive, for example, suppose that a 95% confidence interval for mu1 minus mu2 is -3 to 5. We can be 95% confident that mu1 is somewhere between 3 less than or 5 greater than mu2.